chapter that the chain rule for differentiation run backwards gives you the substitution rule, the W substitution method for anti-differentiation. Similarly, we can run the product rule backwards to get something called integration by parts. So let's see how this should work. So the product rule says that the derivative of, say, u of x times v of x is equal to the derivative of the first thing times the second thing plus, actually this isn't normally how I'd write it, but anyway, plus the first thing by the derivative of the second thing. And what we can do here, so we can just kind of write this backwards, but let's see what it looks like. I think we kind of do it a funny way. Try and look at the formula down below. Yeah, I think we integrate both sides. So I can formally write down something here that if we anti-differentiate u dashed of x times v of x plus u of x times v dashed of x, the x is equal to u of x times v of x. And we do a bit of messing around and you end up with this formula down below. Now what this formula is a little bit more complicated than kind of how it's done there. Like, what does dv mean? And you can kind of do this. So if I say I'm going to basically take this away from both sides, and so you end up with the integral of, I'm going to just write it as u v dashed dx is equal to, I'm just going to write that as uv minus, now this v u dashed dx. And what this v dashed of x times dx is kind of written as this dv. And this is du. So that's what those things actually mean. Well, I mean, it's a bit complicated here. Like, I mean, we kind of manipulate these things. If you remember the W substitution, we do these manipulations that like actually don't make any sense. I mean, dy dx isn't really a fraction. It just turns out what we do with the W substitution, what we're going to do here for this integration by parts formula, even though the intermediate bits are kind of nonsense, it kind of works out in the end. Okay. So this is called the integration by parts formula, or maybe we'll just call it parts. So how does it work? Well, what you have is you have the thing on the left and you have to make a double substitution. You have to pick a u and then a dv. And it's more complicated than the ordinary W substitution method. And usually you would maybe try a W substitution first. Now, the way that you pick the u is you pick it as the first thing on this list. And the reason you do that is because what you're going to do with u is you're going to be differentiating it, which is easy. But with the dv, you need to be integrating the dv. Integral of dv is v, which we'll talk about. And it's harder to integrate than differentiate. So what the Liate rule is about is it's like the way for picking u, but in fact it makes dv lower on this list. So you pick u to be the first thing and everything else then is dv. And these things are in reverse order of difficulty of anti-differentiation. So exponential down the bottom is the easiest thing to anti-differentiate, then trig, then algebraic, etc. So that's kind of the philosophy, as it were, of this picking u by Liate. Now, to be honest, what we need to see here is examples. Okay, so Yeah, so it's not going to say use integration by parts. So we're going to kind of go at this using our strategy. So our first thing is it in the tables? Now, first of all, there's a mistake that you can make, and I'm going to write something and then scribble it out. The anti-differentiation is not what you might call multiplicative. So if you have, say, if you're trying to anti-differentiate u times v, you can't just anti-differentiate u and then times anti-differentiate v. They're not equal. So that's kind of like, say, it's similar with the, like, you have to do a product rule, like the derivative of x by sine x is not 1 by cos x. You have to do a product rule. Now, unfortunately, with anti-differentiation, we don't have something that's as easy to use as the product rule. Instead, we have kind of substitute manipulation, possibly a W substitution, possibly a integration by parts. So what I'm trying to get at here is I've got 5t times e to the minus 3t. I can anti-differentiate 5t, no problem. I can anti-differentiate e to the minus 5t, no problem. But if they're multiplied together, that's basically no good to me. Okay, so I can't do it directly. I can only do it directly if it's a sum. Manipulation means rewriting it. There's nothing really you can do here. In terms of a substitution, you could try a substitution, and the only reasonable shout is to let w be equal to minus 3t, because it's inside the exponential function. And you can carry that through, but you just end up with this thing, which isn't in the tables. You can't do any more manipulation, and there's no w, you can't do another substitution. So the w substitution simply doesn't work. So now you would try integration by parts. Okay, so I think what we're going to do here is we're going to write down the formula for integration by parts and see how to use it. So the formula is written: u dv is equal to uv minus v du. Okay, so what we have to do is we have to pick a u and we have to pick a dv. And my suggestion is that, now I'll put a little thing down the middle here. My suggestion is, yeah, you pick u according to Liate. So are there any logs in this thing up the top in the middle of the page? No. That's the L. Is there, I stands for inverse trigon, like inverse sine or inverse tan? No. A is algebraic? Yes. Now, in terms of algebraic, what you're looking to be doing, that means basically powers of x, or in this case, powers of t. And if you look at the u, it's not inside something else, it's multiplying. So we have to have something that's multiplying, and 5t does the job. Now, some people kind of start doing, oh, the u is the first thing and then everything else is dv. That won't work for you. So we're going to let u be 5t because it's the first thing on the Liate list. So the other thing on the Liate list would be the minus 3t. That's inside another function that wouldn't be the u. So we're going to let u equal to 5t. Okay. Now, if we, similar story, everything that's left then is dv. So dv is e to the minus 3t. dv is e to the minus 3t dt. Okay. So now we need to look at the formula. So in terms of the formula, we have got u. That's good. We need to get du. Okay, and how do you get du from u? You differentiate u. So we're going to differentiate u here, and we get du dt is equal to, now we're going to differentiate 5t, it's a constant times t, fix the 5, and the derivative of t is 1. So 5 by 1 is 5. And if I multiply both sides by dt, which is strictly nonsense but gives me the right answer, I get that du is equal to 5 dt. So I do know what du is, and I do know what u is. Okay, so now when it comes to the dv side of the house, I need to find v. Now, how do you get from dv to v? Now, that's a kind of a difficult question, really. If we used the slightly more correct formula, that dv is actually equal to v dash dx. Let's have a look at that. So the more correct thing really is to say that v dashed, dv is equal to v dashed dx. Okay, and then, well, even here it's a little bit difficult. So I'm going to just write down this. Yeah, so basically what we're doing is playing with symbols. It's hard for me to actually make proper sense of. All I can tell you is that it works. Okay, what I'm going to tell you is that v is equal to the integral of dv, and we'll give, I think I have two ways of explaining that. One of them nice, one of them a different way. So the first way is that integral of dv, well, dv is 1 by dv, and the question is, what do you differentiate to end up with, differentiate with respect to v to end up with 1? It's v. So if I integrate dv, I get v. That's one way of doing it. The other way is a bit nicer, actually. So dv, although actually in this context makes even less sense in a way. So dv, if you went back and studied your integration from last semester, is actually a little bit of v. And integrating dv actually means adding up little bits of v. And the idea is that if you add up little bits of v, you get the whole of v. So however way you're going to do it, you need to understand that v is the integral of dv, however you understand it. Okay, so if we want to get v, we need to do the integral or the antiderivative of dv. So this thing on the left, red and left, that's like integrating dv, and the thing on the right is more like anti-differentiating. So it is a bit confused, and it's perfectly okay to be confused at this point. So where are we going now? So yeah, so integral antiderivative dv is antiderivative e to the minus 3t dt. At this point, you need to go into your tables, and we'll go up the top, or we'll go up here. If you go into your tables, you see that the antiderivative of e to the ax dx is 1 over a e to the ax. And so we can use that down here. We get 1 over minus 3, which is minus a third, e to the minus 3t. And so what we have, therefore, is we have v. So now we have everything for this antiderivative. So look at the orange formula. That's our I above. So I, the orange formula, is equal to u. What's u? Well, we found u, or we chose u, was 5t. What's v? Well, we found, once we chose u, we had no choice for dv, and from dv we anti-differentiated to find v is 1 over minus 3 e to the minus 3t. Minus antiderivative. So now we want to put in the v again there. 1 over minus 3 e to the minus 3t. And what about du? Well, we found from our choice of u, we found du was 5 dt. Okay, so now this, it looks more complicated, but actually the thing in the integral is the antiderivative is easier than what we started with. So this is why it's called integration by parts. If you think about a product rule, if you're running it backwards, you've got two things to anti-differentiate. This kind of plus that. Okay, so what are we going to do here? This integral here, the second one, the antiderivative. Listen, I'm sorry, sometimes I say integral and sometimes I say antiderivative. You can think of them interchangeably. Really, an integral has limits, and an antiderivative is what we're doing here, but it doesn't really, a lot of people will use them interchangeably. Well, if there's limits, they would definitely say integral. Okay, so let's tidy up what we got. So I see 5 here, 5 by t, by, now 1 over minus 3 is minus a third by this exponential. Now they're all numbers, so the order of multiplication doesn't matter. We can do the 5 by the minus third first to get minus 5 thirds. And then by the t, and then by the e to the minus 3t. And a similar, if we look inside in the antiderivative, we've got minus a third, times an exponential times 5. We'll let the dt sit where it is. Now what I'm going to do is, so inside in the antiderivative, the order of multiplication doesn't matter. So I can do the minus 1/3 by the 5 and get minus 5/3. Now that's a constant, and so you can fix the constant. Now let me kind of explain what I mean there about fixing the constant. So you're familiar with differentiation. So for example, if you were differentiating 2 sine x, I have been doing what you fix the 2 and differentiate the sine 2x. So that could be also written as fix the 2, differentiate the sine x. Now, because differentiate, that's a property of differentiation, a part of the property of being linear. Antidifferentiation is also linear, and that means that you can pull out constants out of the antiderivative like you can pull out this 2 from the derivative for basically the same reason. So what I can do is here, inside the antiderivative, I've got a multiple of minus 5/3. I can pull that out and I have minus 5/3, which is plus 5/3. And then I still have the e to the minus 3t dt. Okay, so in terms of this antiderivative here, that's basically just a simplification or manipulation. I've rewritten it. I've just taken out the constant. Okay, so it shouldn't be too bad from here. I have minus 5/3 times t times e to the minus 3t. Fix the 5/3. Now I've already antidifferentiated e to the minus 3t. I know how that goes. It's 1 over minus 3 e to the minus 3t. That's that. And now all I have to do is, well, what's missing? Plus c. So I get minus 5/3 times t times e to the minus 3t. And the 5/3 by minus 1/3 is plus by minus is minus. And 5 by 1 is 5. 3 by 3 is 9. E to the minus 3t plus a constant. Now, if you want to check your answer, what you would do is you differentiate this, and you want to be clear, and you'll notice that you'll need the product rule to differentiate it. Okay, so that's an example. Let's do some more. Okay, so here let's go through our strategy. First is it in the tables? Now, so looking at this, x is there, log of x is actually not there for reasons. So what the hell are we going to do? So we can't do it directly because they're multiplied together. So what about a manipulation? There's nothing you can do here. So what you could try then is a w substitution. Now, you're never going to substitute w equal to x because that'll just replace the x's with w's. It doesn't make any difference. The obvious only thing you could do is maybe w is equal to log of x. Now, what that ends up with is w e to the w dw, and you're kind of back where you started. Well, you're not back where you started. You've just replaced a hard thing by another hard thing. You can actually drive on with e to the w. I wonder if I actually do that. No, I don't. So we're going to do integration by parts. So let's write down the formula. Let's see where we are for space. So integral u dv is equal to u times v minus v du. Right. So that formula could probably just as easily go slightly below. Right. So how are we doing for space here? I think that it works out quite well. I'm just going to write all that again. So integral of u dv is equal to u v minus v du, and we're looking at integral of x log x dx. So don't just assume that the first thing is u. Okay, you go through your Liate. So according to Liate, the first thing on the Liate list is L for logs, and there is a log there. So this is going to be your u. Okay. And everything that's left then is your dv. So dv is x by dx. Okay. Now look at the formula. So we need to have u. We have u, it's log of x. How about v? So we get from... So how did we get v? Well, we said v was the... Now here, I could say antiderivative or integral. It works either way, really. So what's dv is x dx. Now, how do we anti-differentiate x dx? It kind of is in the tables. You just have to recognize that x is x to the power of 1. And so how do you anti-differentiate a power? You add 1 to the power, divide by the new power. So we've got the u. So I'm looking again at the orange formula, in the top left corner. I got the u, that's log of x. I got the v, it's x squared over 2, minus integral. I have the v. What about the du? So how you get the du is you differentiate u. So differentiate both sides of this with respect to x. I get du dx is equal to, what's the derivative of log of x? Go into your tables, it's 1 over x. Now we're hoping to solve this for du because we're looking for du here. So we'll multiply both sides by dx. Strictly speaking, nonsense, but gives you the right answer. So du is equal to 1 over x dx. Okay, so now we're ready to put everything back together. So, integral x log x dx, using the orange formula in the top left-hand corner, is equal to u, maybe I'll use some colors here, u, which is log of x, times v, which is x squared over 2, minus integral v, which we calculated was x squared over 2, times du, which we calculated was 1 over x dx. Okay, so now we have another antiderivative to do. Now the term at the start, so there's a little thing here. So the first thing should be seen as log of x multiplied by x squared divided by 2. And dividing by 2 is the same as multiplying by a half. And there's a possible worry that people might think you mean log of x by x squared, as in log of x by x squared, but that's not actually what you have. It's not the same as log of x by x squared. So a good thing to do here is to, like, log of x and x squared over 2, they're both numbers, so the order of multiplication doesn't matter, so maybe swap them around. So write as x squared over 2 times log x. You don't have to do that, but it's just a good idea. Now what about the antiderivative? So we have a constant there, we have this 2. Now is that a multiplied by 2? Is that a 2? It looks like a 2, but it's actually a divided by 2. And a divided by 2 is a half. So I have a multiple of a half in the antiderivative, I can pull that out. And I'm left with x squared by 1 over x. Now 1 over x is just divided by x. So basically we've got x squared and we've got 1 over x. Now what are you going to do with that? You can't go into the tables because they're multiplied together. So is there manipulation? Can you rewrite x squared by 1 over x? And you can, because 1 over x is just divided by x. So you get x squared divided by x here, x squared divided by x, which is just x. So that's where you go. And that can be anti-differentiated because it's just x to the power 1. So we get x squared over 2 times log of x minus a half, and the antiderivative of x to the 1 is x squared over 2. Now we need a plus c here, but we can slightly tidy up by saying maybe x squared over 2 times log of x. And then we've got a fraction by a fraction. How do you do fraction by fraction? It's top by top, bottom by bottom. 1 by x squared is x squared. 2 by 2 is 4 plus c, and that's done. So you can check your answer by differentiating, and you'll need the product rule. So if you were to differentiate this, you'd need the product rule here because this is a unity. Okay. You don't have to put in the plus c until the very end. Okay. So here's a worked example where you need integration by parts twice. So what happens here is you do your integration by parts and you get to here. So you use the formula, the uv minus v du, And you end up actually needing to do integration by parts a second time. That can happen. Okay, so that's the cartoon for that. So integration by parts, which comes from the product rule, is usually applied to integrands that look like a product. But you don't, now you want to be careful because you can't just there's something here that's not actually been really said. So when you differentiate, or when you're differentiating, basically everything has a derivative in terms of nice things. But like, for example, e to the minus x squared dx, there is a function that you differentiate and you get e to the minus x squared, but you can't write it in terms of any functions that you know about. So what it means is you have to kind of get it out of your head that you can just anti-differentiate everything. They have antiderivatives, but you can't write down formulas for them. Now this is quite a deep fact. And I think all I'm just saying is, like, don't think of anti-differentiation as you got your toolkit of, oh, I'll just use the product rule. It's far more complicated. And I think we had the cartoon quite early on. Where is it? Here. Integration is just far more difficult, and just you want to just think it's not going to be straightforward. And as I said, I'm recommending this strategy that we have here. Okay. Now the reason I kind of make that big deal there is because so I'm saying, oh, integration by parts comes from the product rule, so it'll be a product, but it's a bit more complicated than that. So the 3 examples that we did were do that. But you can have things that don't actually look like a product, like integral of log of x. It doesn't look like things multiplied together, but it still needs integration by parts. You pick u according to Liate, what's left dx is your dv. The other thing is you have to pick the u and dv properly. So I said the reason we have Liate is so you're left, the dv is easier to anti-differentiate. But like, you can't just say, oh, let's just do it so that I'll pick the harder thing to anti-differentiate just to show off. It mightn't work. So a good example of this is with x e to the x. So if you do Liate, so we're down here down the bottom, there's no log, there's no inverse trig. Algebraic, yes, you should pick u to be x. But what happens if you pick u to be e to the x? And what happens is you can still use the formula, but you end up with something that's more complicated than what you started with. Okay, so you do have to pick the u correctly. It isn't just a case of, oh, I'll pick the u so that it's easier. If you pick the u incorrectly, it probably won't work. Okay, so let's do another question, seeing a little bit of that. So here, it's not clear that an integration by parts, surely it's in the tables. It's not. The reason it's not in the tables is exactly because so we can ask questions about it. So now we have an integral, genuine integral here with limits, but what we're going to do is we're just going to forget about the limits initially, and let's just work with this. So pick u according to Liate. So is there a log? Yes. Okay, so there is the L, log is there. So u should be log of x, and what's left dx. So what were we running with before? So let's write down our formula. Antiderivative u dv is equal to u by v minus v du. So we have u, looking at the orange formula, we want to get v. So we get v by integrating dv. So v is the integral of dv, and we said here that dv was just dx. So this is the integral of dx. Now if you add up all the little bits of v to get v, you add up all the little bits of x to get x. So if dv is equal to dx, we can say that v is equal to x. What about the u part business? So we've got the u, we've got the v, we've got the v. What about the du? So we've picked u to be log of x, and if you want to get du from that, you differentiate u. So basically you pick u, you pick dv, you differentiate u, you anti-differentiate dv. That's basically the idea. So we get du dx. What's the derivative of log of x is 1 over x. And to solve this for du, multiply both sides by dx, you get du is equal to 1 over x dx. Okay, so now we have everything to use the orange formula. So we have that the antiderivative of log of x dx is equal to uv. So what's the u? Log of x. What's the v? X. Minus antiderivative. What's v? X. And what's the last thing in the orange formula? Du is 1 over x dx. So now, for similar reasons, you don't want people to think that you're working with log of x squared. It's log of x by x. So to avoid that confusion, write it as x by log of x minus. Now, what about that little antiderivative there? You can't go into the tables because they're multiplied together, but there's a manipulation. X by 1 over x. X divided by x is 1. So you get x log x minus, and what's the antiderivative of 1 with respect to x? What do you differentiate with respect to x and get 1? The answer is x. So the antiderivative of log of x is x log x minus x plus a constant. But here what we're doing is we're doing an integral, so we really don't need the plus c. So we get that the integral 1 to e log of x dx. How do you calculate an integral? You do an antiderivative. So the recommendation is, if it's something as complicated as integration by parts, and you're doing an integral, that you should just forget about the limits, find the antiderivative, and then you see you can do the integral in one line, because how do you do an integral? You anti-differentiate. Well, we've done that already. The antiderivative of log of x is x log x minus x. And now we do top limit minus bottom limit. So put in the top limit, so put in the e for all the x's, you get e log of e minus e, that's substitute top limit, minus substitute bottom limit, so that'll be 1 log of 1 minus 1. You can bang this into the calculator if you want, but I'll tell you what you're going to get. ln of e is just 1, so the first bracket is you got e by 1, which is e minus e, which is 0. Then in the second bracket, you've got log of 1, which is actually equal to 0. So you end up with 0 minus 1 by 0 minus 1. You're just left with minus minus 1. You just get 1. Okay. Now we can get, so what we found here, so this is the graph of, this is y equal to log of x. And we've integrated from 1 to e. And that's, the function is positive there, so we found the area of this triangle here. So what we can actually do is, and that was probably not with that pen, is we can approximate the area using a triangle. Now, looking at it, it should probably be slightly smaller than what we get. So I'm going to try and draw on this thing, and probably won't work well. So I got a ruler on it now. Jesus, could it work? Finally got a bit of going. It's hard to use a ruler with this yoke. It just kind of always messes around. Go on. Oh yeah, sorry, it's not. Look. Go on. Yeah, that's why I don't use the ruler. Look, hopefully you can see the triangle I'm talking about. It goes certainly from, drawing is hard. That's about as good as we'll do. Right, so let's look at this area of this triangle. I will shade it in now just to really go the whole out. So we're looking at this. Don't know if that made any difference. That triangle there. So the area of a triangle is half the base by the height. The base is a kind of a complicated number. So it's going from 1 to e, and e is a number approximately 2.718. Let's just approximate that to 2.72. So from 1 to 2.72, so this should be rough, it's just an approximation. 1.72 times, now the height of it will be 1. Yeah, it's going to be a good bit smaller. You can see the extra bit here that we're missing out on. So 1/2 by 1.72, it gives me 0.86. So that's an underestimate, as you can see. So we know that the area above that line there is approximately 0.14. So if there's a nice picture, you can kind of check your answer of an integral a little bit like that.